Welcome to TM361. The subject of this course is combinatorics. So there's an immediate question. Just what is combinatorics? Well, there's no easy answer. We could say that combinatorics is concerned with relations between objects, particularly when they're arranged in sets in various ways. And that's a part of the truth. We could say that combinatorics is concerned with sets which are usually finite and always discrete. So it's very different from calculus. And that's a lot more of the truth. Now, no one's ever come up with a satisfactory definition of combinatorics. By the end of this course, you will know just what combinatorics is all about. But you won't be able to define it satisfactorily either. Well, we may not be able to give you a definition of combinatorics, but what we can do is to give you something of the flavor of the subject. And just a brief glimpse of the next television program, which happens to be on telecommunications networks, will show you the sort of thing I have in mind. Now, from this telephone, and equally well from yours at home, it's possible to contact as many as 500 million subscribers scattered throughout the globe. Now, just think for a moment what it takes to make all that possible. Now, in fact, the International Telephone System is one of the largest combinatorial structures ever built by man. Now, why do I call it a combinatorial structure? Well, as we shall see, it's made up of billions of tiny units, like these, each unit performing a very simple function. And what gives the system its complexity is not the units, but the interconnections between them. Now, this is precisely the situation in which combinatorics comes into play.
Well, that's one of several excerpts from later programs we'll be showing you today to illustrate just what we'll be doing in this course. As you can see from the title of the course, we're going to be concerned with three main subject areas: graphs, networks, and design. Graphs, where we're concerned with the interconnections between things. London Underground stations linked by rails. Chemical molecules with atoms linked by chemical bonds. Electrical circuits with terminals linked by wires, and so on. And networks, such as a network of streets with traffic flowing. Or the national electricity grid, transmitting electric power around the country. And design, covering such topics as engineering design, architectural design, and so on. And there's also one further area, enumeration, where we're concerned with a wide range of counting problems. Well, counting is easy enough when you've got the objects in front of you, but when you haven't, it can be much harder. For example, how many ways are there of giving change for £1? Think about it. So these four areas, graphs, networks, enumeration, and design, form the subject of combinatorics. But there's another theme running through this course, and that's mathematical modelling. This involves taking the essential features of a real-life problem and representing them by mathematical concepts. In our case, graphs, as in the telephone system in TV2, or networks, or some other combinatorial structure. Solving the resulting mathematical problem may not always lead to a useful solution of the original problem, but it can often shed light on the nature of the problem. Much of the material in this course involves the modelling of a practical situation, such as this excerpt from TV3 involving a traffic problem.
Here in the High Street, there are many fine buildings, some of them dating back as much as 3 centuries. The trouble with picturesque streets like this one is they're just too narrow to cope with modern traffic. There's inevitably congestion. This causes delays for the traffic, hazards for the pedestrians, and of course damage to the environment from pollution, noise and vibration. So Surrey County Council put forward a proposal to build a relief road, bypassing the centre of Godalming and diverting most of the traffic away from these narrow streets. In order to help them in the planning process, the council needed to know just how effective the scheme was likely to be. In order to predict the likely effect of the new road upon the traffic flow, they called in a team of consultants. And I went along to talk to Gareth Jones, who was the head of that team.
Well, as you've seen for yourself, Godalming, this is a map of the area, it does suffer from very high traffic flows down the high street here. It's also the street with all the shops on it. Can't move the shops. Therefore, if you wanted to relieve the traffic conflict, we've got to move the vehicles. And there's been plans to build a relief road round the back of the high street on the manner of this plan here. And we've been asked by Surrey County Council to develop a mathematical model to establish whatever traffic flows on this road.
Gareth Jones then went on to describe the diagrammatic method that was used to produce a model of the traffic flows.
The same thing. These are the entry and exit points around the town, and we have to define every link in terms of its length, the speed down it, for subsequent model purposes. We number each node in order to do this. We certainly have some points where vehicles are starting or originating from within the town, but otherwise it's a fairly standard network. We do here see one-way systems, which is denoted by an arrow. Where there isn't, that's a two-way flow. That we can then modify to put on the new proposed relief road. What we get from that is an indication, from the end of a model process, is an indication of the flows. This diagram shows the flows really. This bandwidth is proportional to the volumes of traffic flowing down the High Street in the morning peak period. There we see 757 vehicles going towards Guildford in this morning peak period. When we've put in the relief road, we see again that the traffic has moved away from the old High Street to the new relief road. If we compare those two diagrams, we can see that the 750-odd vehicles which were flowing down the old High Street have now been reassigned, rerouted to the relief road, 798 vehicles going in this direction and round. The effect of that, as we can see, is that we come from this high flow, 700 plus, in the High Street to only 791 vehicles, leaving the old High Street with just 91 vehicles, which is a very low level and it's no problem for pedestrian conflicts, etc. You could almost turn that into a pedestrian's precinct.
Now, throughout this course, we're going to be concerned with a wide variety of problems. And just as the topics fall under 4 headings, so the problems are divided into 4 types. Now, we begin with the existence problem. Does such and such a thing actually exist? And from this, there follows the construction problem. If the thing does exist, how can you find it? And then we're led on to the problem of enumeration. Just how many of these things are there? And finally, we have the optimization problem. Which one of these things is the best for our purposes? And what we're going to do is to look at examples of problems of each of these types in turn.
Well, first, existence problems. These are really concerned with the possibility of a thing existing. To show that a thing is possible, it's enough to produce a single example of it. But to show that something is not possible can be remarkably difficult. And this is the situation discussed in TV12 in connection with a deceptively simple 4-colour problem. The problem asks whether any map, whether it's the counties of England, the American states, the countries of the world, or any fictitious map which we may care to invent, whether any map can be coloured with just 4 colours, so that no 2 neighbouring countries have the same colour. Notice that countries which meet just at a point are not considered to be neighbouring countries. A is a neighbour of B and D, but it's not a neighbour of C. So it's allowable for A and C both to be coloured red. And similarly, it's allowable for both B and D to be coloured blue. The fact that you need at least 4 colours, and not, say, 3 or 2, can be seen from a map like this one. It's impossible to colour it with fewer than 4 colours. And the remarkable thing about the 4-colour theorem is that it says that these 4 colours are sufficient to colour any map, however complicated. The second type of problem we'll encounter in this course involves construction. It's one thing to know that something exists, but it's quite another matter actually to find it. Often the only way to show that something does exist is to produce it. If it's a mathematical object, that means construct it. Describe it in terms of known mathematical concepts. Finding something usually involves a systematic step-by-step search procedure, and such a procedure is called an algorithm. A good example of the use of algorithms is shown in TV5.
We are at an assembly plant in Bedfordshire. A completed truck rolls off this production line on average every 15 minutes. Now, this rate of completion can only be kept up if there's a steady supply of parts and if each of these parts is fitted to the trucks at the right place on the line. Well, to give you some idea of the scale of the operation and of the need for good scheduling, let's just take a quick look around. A frame enters the factory, and on this section of the conveyor, it is married to the axles and the wheels and tyres are fitted. Next, the brake systems and prop shafts are fitted. After these have been checked, the engines are installed. The trucks are then raised to a higher level and various parts are assembled underneath the chassis. Notice that we're dealing with a continuously moving conveyor. If the conveyor were to stop for any length of time, the manufacturer would suffer an expensive loss of production. At this stage in the process, the cabs are married to the chassis and electrical and braking system connections are made between the two. After a number of further stages, the assembly is complete and the vehicles are then subjected to a number of tests. Now, that was a very quick look, and we've missed some important stages. However, we've seen enough to make it apparent that a lot of thought must have gone into the planning of the whole operation.
The Programme Planning Manager went on to explain to Roy some of the flowcharts he used, leading to this production diagram.
Activities that form a network diagram. Now, in this diagram, we are adding the durations of those activities, in this case, in units of days. If we were now to follow the various paths through the diagram, summing the durations of the activities, we would eventually arrive at the longest time path between the start and finish of that diagram. If one was to calculate it for this particular network, the longest time path, in fact, is through that sequence of activities.
Well, that's an interesting thought. How do we set about finding a longest path? It's easy enough for a simple network, but what we really need are algorithms capable of dealing with networks of any size. Now, Norman Biggs of Royal Holloway College is going to look at this problem in mathematical terms.
One of the many practical applications of graph theory is to provide a precise framework for the kind of ideas that John and Roy have been discussing. Here's one of the networks they were talking about. It's a version of the die-making network. You'll recall that the individual jobs are represented by arcs, and the relations between them are represented in a fairly natural way. Let's suppose we have 3 jobs, A, B, and C, and A and B must be completed before C can begin. Then they'll appear in the network like this. For example, the punch and the spotting aid must both be constructed before they can be bedded together. So, in mathematical terms, we have a digraph. The arcs of the digraph represent jobs. Each one has associated with it a number representing the time needed for that job. The vertices of the digraph represent events, or perhaps we should say non-events. Each one marks the end of certain jobs and the beginning of others.
Norman Biggs went on to explore some of the interesting consequences of this representation. Now, enumeration is not only one of the subject areas of the course, it's also a type of problem. Enumeration as a type of problem arises when you've already solved the existence and construction problems, and then ask if there might be more than one solution, and if so, how many solutions? Sometimes it may not be at all obvious that a problem does involve enumeration, and an example of this occurred in TV4 in connection with the behavior of liquid helium.
That liquid is boiling away there, even though it's unimaginably cold. In fact, this is the only material which remains liquid at such low temperatures. It's liquefied helium gas, and its temperature is within a few degrees of the lowest possible temperature, absolute zero. I've come to the Clarendon Laboratory here in Oxford, which is one of the world's leading low-temperature research laboratories, because there are some remarkable properties of helium that we want to look at today. And it's going to turn out that these properties can be interpreted in terms of the counting procedures that we're going to discuss in this course.
The properties of liquid helium can be explained by the special way that atoms may be counted. Later in the program, I went on to illustrate the different counting procedures one might use. I'm going to assume that I have 5 pigeonholes, and I'm going to distribute 3 objects among them. And first of all, I'm going to assume that these 3 objects are distinguishable. That means we can tell them apart, like these differently coloured balls. Well, let's put the first one in here, and the second one in here, and the third one, we'll put that with the red one in here. The question is, how many ways are there of doing this? Well, there are 5 possible positions for the first ball, 5 for the second, and of course, 5 for the third, giving us a total of 5 times 5 times 5, which is 125. And in general, if we have n pigeonholes and k balls, then the total number of ways is n times n times n k times, and that's just n to the k. So the number of ways in this case is just n to the k. Let's see what happens now if we allow only one ball in each pigeonhole. In this case, the first ball can go into any of the 5 pigeonholes, the second can go into any of the remaining 4, and the third can go into any of the remaining 3, giving a total of 5 times 4 times 3 ways. That's 60, which is less than half the number we had before. And in general, if we have n pigeonholes and k balls, then the number is n times n minus 1 times n minus 2, right down to n minus k plus 1. And we call that n sub k. It's equal to n factorial over n minus k factorial. So the answer is just n sub k. And that deals with the cases where the balls are distinguishable. I then went on to examine the other possible counting methods as well, to see which one applies to liquid helium. The last of our 4 types of problem is that of optimization. If you know something exists and can find it, and if you know how many things exist and can find them all, there still remains the problem of choosing the best, according to some criterion or other. Sometimes you may have to settle for the best result that can be achieved in the circumstances, as you'll see in this excerpt from the program on undersea gas pipeline systems.
But now, the edges of the graph are pipes which lie along the seabed, channeling the gas or oil between the rigs or main feeder lines to the shore. The cost of laying offshore pipeline is considerable. In 1980, it was around £750,000 for each mile. And there were 2 types of technology in common use. The more traditional method of pipe laying uses supply boats to ferry sections of pipe out to a lay barge. Now, this operation requires many vessels. The floating supply boat has to be constantly restocked by smaller boats from quayside stocks on shore. The other method, which is used only for narrower and more flexible piping, employs a special technique in which the pipe is joined together and wound onto a large reel. The ready assembled pipe is then carried out to sea by a special cotton reel boat, which itself is a very expensive investment. Starting from one of the rigs, the pipe is unrolled from the reel and it's gradually fed down to the seabed. With both types of pipe laying, the processes involved are complex and costly. The pipelines, which have to be buried beneath the seabed by special trenching techniques, must endure for many years and be well sealed and stable. They must withstand the effects of the pressure and the corrosive elements of the sea, and much attention is given to the joining together of pipe sections. The pipes are coated, beveled, and carefully lined up before going through up to 6 welding processes. Rigorous checks are made at each stage, including the use of X-ray film. The joins are then wrapped with an adhesive primer layer, and a steel sheet is strapped over them before they're filled with melted mastic and finally laced up ready for use. Now, although both types of pipe laying are expensive, the broad diameter pipe is a more costly commodity, and any savings in both diameter and overall length of pipe can soon run into many millions of pounds. So it's this choice of pipeline layout and pipe diameter that is the centre of our problem.
The task of designing a good undersea gas pipeline system was one faced by Dr. Howard Frank of the Network Analysis Corporation in New York, who explained his approach later in the program.
Problem breaks up into 2 fundamentally different problems. The first one is, suppose I had this network. Suppose, for instance, I knew this was the network I was going to build, this exact tree structure. First problem would be to determine the costs and associated diameters of each of the pipes within the network. To do that, I would have to design the network in such a way that I met the crucial variable, that is the pressure constraints at the gas fields and at the onshore collection point. For example, if I delivered the gas with a very low pressure, then I would have to spend a very large amount of money at the onshore point to recompress the gas for transshipment in. If I delivered the gas at a very high pressure, because of the fluid dynamic equations governing gas flow, I would have to spend a very large amount of money for the actual pipeline sizes themselves. So consequently, my design problem is a compromise of picking the right size diameters to meet the pressure constraints with the minimum cost. If I could solve that problem, I have a second problem. That is, what is the proper arrangement of pipelines in terms of locations? For example, I have a pipe going from here to here. I could just as easily have made that pipe be replaced by one going from here to here. Selecting the right topology, that is, the right configuration of pipes, is itself a difficult problem. If you can't solve the first problem, then you clearly can't solve the second problem. So we decompose the problem into 2 separate problems. First, the design of the diameters. Second, the actual design of the configuration of the network. In doing so, we utilize the fact that this is a tree type of structure. And in fact, the major breakthrough is recognizing that it was a tree, and a tree had certain properties that general networks do not have.
Dr. Frank told me that savings of many millions of dollars were made in the design of undersea pipeline networks, simply by applying combinatorial techniques. Now, in looking for real-life examples, we've had 2 aims in mind. First of all, motivational, to stimulate your interest in the theory behind the example. And secondly, practical, to show you how to apply the theory in modeling the sorts of situations, or at least some of them, that you might come up against yourself. Well, I hope we've given you some idea of the sort of thing you're going to meet in this course. Taking the television programs, the texts, and the cassettes, you'll find that there's quite a wide range of topics covered. Now remember, the television programs are an integral part of this course, and they include a lot of material that you won't find in the written text. So do watch, won't you? Good luck.